This two-variable function f is a composite function. The outer function is the exponential function, which is a single variable function. The inner function is x squared times y, which is a function of two independent variables x and y. This is what makes f a multivariable function. So, how do we compute the partial derivative of f with respect to x? Let's first step back a little to consider this single variable function. The only change that I made is replacing the variable y with the constant 3, and so the inner function becomes a single variable function. For sure, we know how to get the derivative of this function. Use chain rule. Now, let's put the two functions side by side and simply replicate the result of applying the familiar chain rule accordingly. The only things that don't look right are the two ordinary derivatives. So let's fix them. Here we go. This is how chain rule plays out for this particular kind of multivariable composite function. Great, but I think I owe you a justification. Well, I didn't blindly clone the result indeed. Look at the two composite functions again. They both have a single variable function as the outer function. So, we can reasonably expect that the first part in the chain rule for the two-variable composite function f should still be an ordinary derivative of the outer function. As I hinted a little bit earlier, the only thing that makes the two-variable case apparently more complicated is the inner function, which takes another independent variable y, and the good old chain rule says that we have to differentiate the inner function as the adjustment for the outer function. So, it makes sense to replace the ordinary derivative in the second part with a partial derivative. Alright, let's pick up where we left off. The derivative of the exponential is itself, so we have the outer function e to the power of u evaluated at the inner function x squared times y in the first part. To compute the partial of the inner function with respect to x, we hold y constant. So factoring y out of the partial, we end up with differentiating x squared with respect to x, which is 2x. Altogether, the second part is 2xy. Last but not least, we plug the inner function into the exponential function. The first part becomes e to the power of x squared times y. Finally, partial f partial x is 2xy times e to the power of x squared y. Now, let's compute the partial derivative of f with respect to y. It's going to be a very similar process. Again, we start with chain rule. The first part is just the same as before, only the second part is slightly different. Here, we have the partial of the inner function with respect to y. So holding x constant, we factor x squared out of the partial, and we end up with an ordinary derivative of y with respect to y, which is 1. So the second part is x squared. Multiplying the two parts, we have x squared times e to the power of x squared y. Alright, let's try another one. Here we have a product of two functions. The first one is simply x. The second one is ln of 2x plus y. Notice that the second function is a two-variable composite function. The outer function of the composite is the natural logarithmic function, so single variable. The inner function of the composite is 2x plus y, two variables. So we are dealing with a multivariable composite function of the same kind. Let's start with computing partial f partial x. First step, we apply the product rule. In the first term, we have the composite function multiplied by dx dx, which is 1. In the second term, we have x times the partial of the composite function. So here comes the chain rule again. The first part is an ordinary derivative of the outer function evaluated at the inner function. The second part, which is the adjustment for the inner function, is the partial of the inner function with respect to x. Differentiating ln of u, we have 1 over u. To evaluate the partial with respect to x, we hold y constant. Now we are differentiating something like the linear function 2x plus a constant, so the partial is 2. Now let's organize what we've gotten so far. Here is the first term. And the second term is x times 1 over u evaluated at 2x plus y times 2. One last step. Plugging 2x plus y into 1 over u, we have 1 over 2x plus y for this part. Finally, we get ln of 2x plus y plus 2x over 2x plus y. Okay, as the final practice, let's compute partial f partial y. First thing first, again, product rule. Partial x partial y. This is 0 because we hold x constant when taking partial with respect to y. In the second term, we have x times the partial of the composite function again, but this time with respect to y. So again, we need chain rule. The first part is the same as before. Remember, the first part of the result of applying chain rule depends only on the outer function, which is a single variable function of some dummy variable u. The second part becomes the partial of the inner function with respect to y. Treating x like a constant, we are indeed differentiating a linear function like y plus a constant. So here we have 1. Gathering all the pieces, here is the first term. Here comes the second term. Indeed, only the second term survives as the first term vanishes. Plugging the inner function into 1 over u, same as before. So partial f partial y is x over 2x plus y. All right, this is it. I hope you enjoy the video, and don't forget to keep practicing. See you in the next one.